Yeah, here are just some examples for similarity measures. Only a few, very few examples. There are a lot of more examples, of course, out there. So, for example, you can use the dot product as a kind of angle between two vectors. Yeah, we have two vectors, so we always assume that the feature representation is really a feature vector in a n or d-dimensional feature space with real valued features. Then of course we can, so the x and y are points in a high dimensional space, in a d-dimensional space in that case. Then we can just use the dot product as a kind of similarity model, yeah? Or we can take the cosine between the two vectors, yeah, which is given here, or the Pearson correlation coefficient, which somehow measures the correlation between the individual feature values with each other. Yeah, so we compare the individual feature values of x with the mean vector of x, yeah, and the individual feature vector values of y with the mean vector of y, so to say. Yeah? And so that somehow measures the correlation between the individual features in that case. Yeah? Or we can apply kind of random walk kernel for graphs. So now in that case, x and y are not feature representations, but we can still work on also, of course, on different representations. So for example, directly on graphs. Yeah? So random walk kernels would be, you count the common random walks in x and y. Yeah? So you just walk through x and y in a random order, yeah, starting from a random node in x and then from a random node in y, and then just go through the edges, yeah, in a random manner, and do that many times, and then the walks are sequences of nodes connected by edges, and then you see, do I have or count the number of common walks in both of those two things. Yeah? If you do that many times, then if x and y are similar graphs, yeah, or have similar substructures, then you will probably have a lot of common walks, a lot of common paths among those random walks that you did. Yeah? And if not, then of course not. Yeah? So counting the number of, or simply counting the common random walks is a kind of similarity measure in that case. The more, the better in that case. Yeah? So those are just some kind of examples for similarity measures, and of course we can have some distance measures, also some examples, also only very few ones. So you probably also, again, of course, already know the LP norms, also known as the Minkowski matrices. So that is the general formula, and of course you know it for p equals 2. It will be the Euclidean distance, because you take the individual, that should be xi, of course, here. So you take the individual dissimilarities to the power of p, sum that up. So in that case, for p is equal to 2, you take the square, sum that up, and take the square root. Yeah? That is the Euclidean distance for p equals 2. For p equals 1, you already know that's the Manhattan distance probably. Yeah, you can even take a p which is smaller than 1, then it's a so-called fractional Minkowski distance. You can just play a little bit with that. So that the choice of p doesn't really make a big deal typically. Yeah? And if you just take the maximum, which is denoted by p equals infinity, then it's the maximum distance, or also called sometimes Chebyshev distance. Yeah, other examples, Mahalan-Lobis distance, we'll talk about that later on again. Also Hamming distance, of course, where you just have a look at features. If they are exactly the same, then you take a zero, take a zero, sorry. And if they are not exactly the same, then you take a 1 and sum those things up. Yeah, which is a very coarse distance, of course. Yeah, because you don't count, or you don't quantify the dissimilarity, the distance between the individual features. You just record a 1 if they are not the same, and a 0 if they are the same. Yeah? So that is a very coarse. So Hamming distance is always a very coarse distance, because it just penalizes dissimilarity distance with 1, and similarity or equality actually with 0. Yeah? Okay. So yeah, and now let's have a look at the most important challenges that are coming up in high-dimensional data, and we'll see that this is actually there are actually a couple of those challenges coming up. Yeah? And maybe you also already know the term cursive dimensionality, and we'll talk about the curse here, yeah, and see what can actually happen in high-dimensional data. So. First of all, I usually talk about is the very motivating example, especially for students, I think, the baby shape game. Let's play the baby shape game. Why not? Huh? Okay. So the question is here: you have a couple of items, toys or whatever, and you ask a baby or a group of babies, please group them. Yeah. And well, probably it's some kindergarten kids, but anyway, and the kids are doing different actually. Yeah, so some group those items here based on the shape of the items, and some group them according to their color. Yeah, and the question is, what is the correct one? Well, actually, somehow both are the same, or both are actually acceptable. Both are somehow correct in some sense. Yeah. Well, the problem why both solutions are actually absolutely fine is that here in this application, in this data, we have two different semantic concepts, and their corresponding patterns that's what the babies or the kids are actually producing. So the two different semantic concepts here are color and shape. Yeah, and you can group the things here according to shape and according to color. Once again, these are two different semantic concepts. And some kids just took one specific concept, color, for example, and those kids just took the other concept, semantic concept, which is shape. Yeah, and that can happen very often, especially if we have a lot of features. So if we have 100 features, it may be, I mean, that's a very artificial thing, but I hope it somehow illustrates what can happen. You may have 50 features that represent color and 50 features that represent shape. So now, if you, for example, doing clustering, what do you want to have? Do you want a clustering according to color, or do you want to have a clustering according to shape? The same holds true for if you want to, if you have labeled data, maybe you have, of course, for example, labels according to the color, then the 50 features representing the color concept are important to your application, to your classifier, to your learning. The other 50 features for shape, representing shape, they are not important, of course. But these 50 other things that are not important probably harm you a little bit, yeah. And we will see how they actually harm you. That is the first lesson to take away, is that we may have different semantic concepts. So some of the features may have a completely different semantic meaning, and they somehow just do not represent what you are actually searching for. Yeah, they are absolutely irrelevant for the features, for the patterns that you want to describe, or you want to explore, or you want to find. And the question is how to deal with that. The question is, how do they really harm you, or can we just ignore them? And well, you probably already think or somehow can think of the answer to this question. We probably cannot just ignore them, yeah? But we'll see why that's the case actually.